Hello, welcome everybody. This is Professor Mascarella. I am here to share with you the progress that my company EKATRA has made on digital twin and real-time monitoring of strategic assets. So the presentation I'm sharing comes from the Fog World Congress. Are you familiar with fog? No. So you have a typically two computing model. There is the computing model that is everything is client server on premise, and there is the cloud-based computing center. Now there's this new computing model, it's called fog, based on nodes that talk to each other, and both, sometimes are in the cloud, sometimes we are distributed. It's also called edge computing. And fog is the standard that the consortium that is writing the specification to reach a certain level of quality. As a matter of fact, fog was able to submit and make a standard edge node computing in IoT. The standard is IEEE 1934, and EKATRA is compliant to IEEE 1934 as architecture. So what we're going to talk today is what is EKATRA, what problems we solve, and the digital value chain. So let's look at the value chain. At the first step in any IoT solutions, you need to ingest data from assets through sensors, and the capacity to ingest data fast, it's very important, especially if you approach it near real time. In our software, we do 500,000 data points per second. And the challenge becomes the other, it's how do I handle a huge volume of data, especially when it's streaming almost in real time. So you need to move from just a fast ingestion, that is an achievement, to something more interesting that is contextual awareness. That means you correlate and enrich with contextual data what you are learning. So typically you get a 3D representation of the asset you are monitoring, and you give the opportunity to have data points for every components, and you can also have colors to show, like in normal color is normal condition, in yellow it's condition of interest, in red you are in emergency. And the way we do this is we use machine learning to assess what is the expected value of every of these data points and sensors. Because what is important is the delta between the expected value of this temperature, this power, this volts, and these conditions, and what is the reading. But even that difference is not important if you don't put in the context of what are the value, what is feeding, and is due to this component or is due to other components that is generating some problem downstream. So this contextual data is also called the digital twin. So digital twin is a representation of an asset with the data coming from the assets, and the relationship is generally one-to-one. And that helps to make the better decision about how to intervene to maintain the health of the asset and increase the RUL, the remaining useful life of the asset. But this is not enough. What we did is we developed an additional layer of software that is called situational intelligence. And what does it mean? If you have a situation where this is in yellow and red, you might want to make a decision, but sometimes if those are critical assets, like a power transformer that might shut down an entire shopping mall or a manufacturing plant and so on, or a chemical plant that could, an anomaly could lead to the spill of chemical elements into rivers or other places or in the air, then it's no longer your decision. Your decision needs to be shared with the stakeholders, the fire department, the emergency response, the FEMA, all the people that need to be ready and monitor the solution. Because very often, a lot of places continue to operate in a condition of interest. And their capacity to have collaborative decision around a digital twin is what we do. So you have a mission control room with dozens of screens where anomaly detection for machine learning will pop up a number one situation of interest, and you can decide, well, sometimes you don't decide the emergency response have access with data, but sometimes you can decide to share this and notify the fire department of emergency response and make a decision on how to handle it. At that point, you have involved all the parties into the value chain, sometimes even consultants or the service company that did the last maintenance. You want to get them into the decision. So this one becomes available 4, 5, 6 parties. The compliance authority sometimes wants to know what is going on. And at that point, the situation allows decision on how to handle situation of interest more effectively than the local plant people. All this is for the present, but as we know, we have a mathematical software tool based on machine learning where you can predict. So how about we go into predictive analytics, where you say, given the current condition, we predict that in 3 hours, 3 days, 3 weeks, this is the condition is evolving. We also can predict the diagnosis. And so at that point we start applying machine learning, and that's where the game becomes even more exciting, I would say. The last step is when you go in the prescriptive. It means that you trust so much the system has been tested so much, for which you let the machine manage the machine and make decisions without human intervention. That is something that is happening as autonomous driving, for example. So it's not sci-fi, this is a reality. Autonomous car exists and the driver doesn't need to make a decision, machine talks to machine. And so that is the journey into data, to digital twin, to situational awareness and management, prediction, and that's what we're going to go deeper today. So the first thing is, how does a software produce a digital twin? You need to have a typical 6 components, and the EKATRA does this. The first component is the sensor side. It means you need to interface standards like SCADA, OPC UA, Modbus. And those standards are very different from what you need. For example, SCADA is a very simple protocol, but it's common to almost every device in the world, every industrial brand. At the same time, it's also old, therefore you have an old system that can talk to SCADA. OPC UA is a way richer protocol. It really has tools and interface on management very sophisticated, but at the same time it's very recent and not every machinery supports it. Then you go into sophisticated protocol like Modbus, that it is real advanced. It monitor real time. For example, cars could be a protocol in which component talk is a Modbus, but it's very demanding in terms of bandwidth, memory, and so on. But the performance are amazing. It's secure, it's fast, it's reliable. But you gotta see when you need to have that level, and not when OPC UA is not good enough, for example. And then there are many others, but those 3 are the top. You should be aware. So this is the component where you access programmable PLC, programmable logic controller, microcontroller, sensors. Sometimes a dApp, just transmitting data. Sometimes sensors have intelligence and act, close the valve, do something about that. And that is pretty much interoperability with protocols and devices, and verifying that the devices are correctly reading the data. That is one element of the node. The next element is that you take all this data, and the first is you save with the timestamp so you can do an investigation, but at the same time you need to take the data streaming, and the metadata means that you can't ship all the time. This is the part A, B, C of the pump inside, the concentrator inside, the building 3 inside building 4, and was repaired this on January 3rd, and these elements was replaced. All this is not work. There are data you need to separate, and you say that what is changing is the reading of these 2 values. So you need to stream those 2-3 values and put them together with the data about the assets and the situation and the representation of the element. So all this orchestration of data, metadata, timestamp and so on is the components called data management. This is also a very delicate part because you have a massive amount of data. Very often they're not structured like SQL data tables. They are unstructured or semi-structured. So here you might end up having things like Hadoop HDFS, data lakes, very exotic, multimedia. You know, if you have an infrared reading multimedia, it's not SQL Server. Those are really complex images that you need to serve in a way that machine learning would understand. So that is what you do in this way. The next element of a software provided digital twin is a graphical user interface. In the sense that you need to have some library of 3D elements, otherwise you do want to reprogram from scratch all the elements possible you need to read and represent an asset of mechanical elements. You also need to have a dashboard with a pie chart design, tables, you know, all that is part of the human interface. Sometimes this is also virtual reality or augmented reality. That's all. This one, for example, very often writes on blockchain, interactive blockchain. This instead is just the opposite. It's text data, represented data. The next layer is the machine learning, and there are plenty of libraries that will help you forecast, predict, classify, do anomaly detection, and that's a science in itself. There's a module in this way, and so on. When you go number 5 is the business app. This is because a software that manages a digital twin needs at the last mile some intelligence about a power transformer, a fuel tank. What are the regulations? What are the meaning of certain events? So that layer of understanding the business of the asset in the installation is a business app, and this is generally developed with the people that do maintenance of the asset. While the rest is software, this is very sensitive to practical experience of the asset or the manufacturer's recommendation of operation and so on. The last layer is the ambulance. If you have a problem, how do you go and fix the orchestration? How do you distribute the workload against nodes? For example, EKATRA is built under edge computing, so every node has all the services, and you decide this node that is close to the sensors is 80% this and 5% the rest. Or you can have another node that is just a big database with a big storage area network, and therefore is 80% storage and 1% sensors, because in reality you're managing data. Now these nodes also talk to each other as a publisher subscriber, in the sense that I can publish data and give it to somebody else, or sometimes I can ask data, say I have a situation of interest, I need to compare this to the data from the other, I don't know, concentrators at this moment, and you go and ask those data. So those nodes switch roles or can have multiple roles at the same time, and can also have different configuration. You, in an emergency situation, you might give a lot of CPU and I/O to a certain process and to give low quality of service to others. So those are all the elements that security orchestration will handle. Do you have any question about how a software needs to be built to really produce a digital twin?
I just want to ask you, so when you said machine-to-machine talking, so let's say the sensor has the rule, if it's under whatever degrees Fahrenheit, it's bad. So then the other sensor would be the turn-off switch, right? So then once it reads that it's under something degrees, it will just automatically turn off and provide that decision. So you don't need a human to...
It's not that It's simple to say you turn off or you turn on. You provide the information. Very rarely they
I'm saying it replaces the human that's looking
well,
at it. That's
yeah, it
monitoring.
replaces for sure the human that reads the value. There's no longer people taking notes, going
Or
to
it
the
does
office.
nothing because it can do it itself.
Yeah,
It knows when it.
you take the data from the device, you know, and from the sensors. And it's quite interesting. There are sensors today that can smell gas even better than humans. There are sensors that can tell you the saturation of a certain ethanol and gas within a gas station and tell you when the saturation is approaching a situation of interest. Because you know what? The fuel doesn't catch on fire. It's the fuel mixed with air that catches on fire. So saturation of fuel in the air is more important than a spill of fuel. So those are the kind of things that you can collect data 7/24 till you have a situation of interest. Suddenly there is an increase on saturation. Is this a pipe leak or is something else? Those are the things that we deal within this software. What problem do we solve? The most common problem we solve is that as the amount of intelligence on an asset increases, so we go from data that tells you what happened yesterday to what happened 10 minutes ago, to data that says what is happening now, and I can query the data. Give me the data of this, take away that. Or give me the data of the maximum value reached in the last 2 weeks and compare this with that. So that kind of manipulations gives us insights that as these insights increase, you have the cost of incidents and maintenance decrease, and the overall equipment efficiency increase, because you go from having multiple unexpected events, a fragile reactive situation, to have more proactive intervention and say we see a trend on a possible leakage. This is manageable till this day. After this day it will be dangerous, so you intervene the day before pretty much. So you transform for what is called preventive maintenance, means like in your car. You change the oil every year, either if you need it or you don't need it. Instead here, you change the oil when you have done all the things that make the oil no longer fit to support the task it's supposed to do. So these signs of decreasing the cost, increasing the performance as intelligence increase is what the digital twin is targeted and designed for. So how does it look? If this is a turbo generator or an electrical plant, that's what we do generally, this is what a digital twin looks like, and instead of the name of what it is, it has the value of the temperature here, the watt, the magnetic fields. And for example, if this is the rotor inside a turbo generator, actually this is rotor stators here both, you took A, B, and C, 3 sections, and you look at the data of temperature, and then you can look at also other data that is the voltage, the power going through, and then you say for this voltage, amp, and power going through, the temperature here, it's an anomaly. This means that might be some windings losing the insulation and is overheating. There's many things that can happen in this world. Now, let me share a demo of a real digital twin. So this is accessing real data in a situation of not interest, of course, but if we...
That's how the dashboard looks?
Sorry?
That's how the dashboard looks?
This is the dashboard. This is at the very high level of what is going on. And then pretty much you click on, this is the rotor and stator of a turbo generator. And for example, there is one winding that is giving some anomaly detection. You know how this works. You know, you have windings, magnetic fields on the part that doesn't move, the stator, and the part that moves. The difference of the magnetic field produces electrical energy. Now, the movement, the rotation, is generated by some steam gas that goes through and pushes the internal part to move, and then this frictional magnetic field. So that is what you see. You have for every winding all the values here. You can also look at just the rotor or just the stator. So those are all elements of a demo of what can be done with a digital twin. Of course, you have more technical data, but at this moment, we're not going to dig into the science of a power generator. This is a meetup about the software, so we're going to skip that part. What I want to talk about is instead something that caught our attention, and where can a digital twin save the world? And you might be familiar with this. You see on the state, those are transformers. Transformers, very briefly, bring energy from 1000 volts to the 220 that comes into your restaurant, the 110 that comes inside your house, but also adjust other things, frequency. For example, a transformer on a boat, every port they go, they have a different voltage, different frequency, different power. We clean the energy, we make it usable. So in the United States, there are over 500,000 of this that are supposed to be replaced because they were deployed after the war in the 50s and the 60s. They break very often, and in certain cases, like the wildfire in Campfire in California, were the cause of the death of a lot of people, and one of the biggest wildfires ever seen. And there is no budget to replace them soon, because to replace those, it's very expensive. No, the asset is expensive, but sending a crew of workers to deal with high voltage, because a lot of people die in this situation, it's very expensive. So
would it be a downtime too?
Yeah, there is downtime. What people do generally, they do redundancy, they keep adding more, and when the one goes down, the other goes up. So if you could spend only, let's say, 1 million, instead you spend it 2 or 3 million, because, for example, in shopping mall, other than monitoring a device to work well, to last, and do the right intervention, instead of buying one, we buy two, and instead of monitoring two, we buy a battery. So if the first fails, then we use the second. The second fail, very often fail because nobody knows that after so much time you have not used it, if it's really usable, then we go to battery till we fix what to do. But then the intervention in a very high voltage risky environment is very expensive. An intervention on a transformer, just the service call there, is something like $1,000 just to show up, and then it goes to $5,000 very easily. Actually, here in Miami, a month ago, one guy from a service company died in one of these condos who was trying to troubleshoot a transformer, and we found him dead. Nobody knows what happened, but in a normal service call, he died. Now, EKATRA, in this case, with digital twin, will reduce the EOS time, because those people go with the truck there and try to guess. We have no clue what happened, we have no data, and it's surprises. That's the only thing we can guarantee. The next is, they go there, on average, they have $70,000 to $90,000 of board equipment in the truck. And they tell us that on a 50% cases, or even more, the part is needed is not in the truck. So there is no reason why we have 90,000 in the truck, and plus we need to go back. If you have data from a remote monitoring, you will go there with the right part, with the right knowledge, with the right technician, because sometimes somebody expert in winding is there, in reality the problem is the electronic board, so you're going to send another different crew to handle this. Reduce risk of casualty, because when you don't know what is going on is when you die. increased performance. You know, if you do the right maintenance, you get the clean current that you require. Now, we are applying this to transformers that are not the same. Some transformers like this are based on oil. You see there's a tank, and the oil is the cooling system, the isolation system. Some are air-based, some are forced air. In the case of oil, what generally happens is that when the winding is no longer insulated, when things are not working, the electricity creates gases. And depending on the quantity of gas, you know how soon the transformer will fail. And that's what the science today. You know, there's a man, goes there, takes a sample, sends to the lab, 2 or 3 days later say, you found this gas, you have this problem, change the oil first, but also go and change this and that. And generally, from the moment the person was dispatched, when you intervene, it's months. Instead, the software we built, we look at not if there is gas, but look at how was the gas discharged. Was discharged in a slow manner? Was there a burst? Was there like intermittence? By understanding the patterns, you can figure out if you need to change some insulator, the plates, the winding. So you use stuff. Now, we have done some prescriptive in terms of understanding the logic of the relationship from but we are also looking into machine learning where this logic doesn't need to be told. The machine learning, we look at the data of the last 5 years and say, you know what, given what I learned from the past history, you can say with 80% accuracy that this is going to be a case of insulating material replacement. And then 50% is a winding problem, and 10% is this. Of course, you don't send the truck for the 10%, you send the truck with the fixed probability 80% or 60%. That's the way a digital twinning can really help you to create value. So we did this for digital transformers, and actually we are in the middle of doing this work. But this could be done for others. We have a client that asked us to do this on the quality of the oil going into industrial equipment. Like if you have a turbo generator, very often every hospital, every shopping mall has a turbo generator as a backup, and so on. Well, if the lubrication oil is very bad, the turbo generator will fail faster than you can think about. So we're looking to Caterpillar, big machinery. There's plenty of scenario where the fuel and the oil monitoring, it's also another interesting thing for safety and for the quality of the service. So this is a view of the single asset. Now, let me give you a demo of something seen within the context of a larger scenario. So this is a diagram, a digital twin of a manufacturing process. And for demonstration purposes, we masked the real case, and this is representing a chocolate factory. And you can choose the line, the zone, the machinery. This is a situation for the grain breaker where we predict, so we monitor the performance of the grain breaker in its key performance indicator. And generally, you have the control chart, means that when the condition of the vibrations machines between 80 and 110, you are within the service level agreement designed to work. Now, if we look at other machines, for example, if we take instead of the grain breaker, we go and we look at the turbine dryer, then what we see is, we see is that, why is it doing that? It's supposed to stick to this point. I won, did what I want. So if we select this other machine, we see that there's a trend. And then with machine learning, we project the situation, and this is not random, but all the elements as a loop continue. So before you hit the situation of outside the service level agreement, you want to do an intervention. But what intervention you do? That's the question. So what you do is anomaly detection, and you see when this happens, is all the time. We discover there's like a dozen times. The next thing is, are those all critical or not? So those are vibrations, and some are high, some are medium, some are low. The next thing is, given the data we know, what are the forecasts for the entire process of mathematics or machine learning? And here you see that, for example, bearing M1 and M2, we have like probability of failing 30, 90, 100, 360 days that are very below 50%, so no big deal. While blades have 100 days, 80% probability of failing, and gets almost 90 in 360 days. So there are things that are situational evolving with a high probability. There are things that pretty much you don't need to keep changing and lubricating the bearings that compared to other things are not doing. Now, why you look at this is because from an operator point of view, you need to take this control. But from a performance, you need to have a production through output at a certain level, quality and uptime. And for example, here you define what is bad. Between 0 to 200 parts per hour is bad, and between 200 and 600 is average. 600 to 800 you are performing very well. Now, the next question I have is, if I'm in this situation with the blades, can I zoom in and go from the voice of the process to condition management? So if we move to condition management, you zoom into the condition of vibration, and you see that compared to the expected vibration, you have certain vibrations that are different. So that different vibration leads us to look at the harmonic of vibrations. And generally you see those two harmonic, but if you look at a period that includes the time where we had the very high, so we expand here. So we saw from the previous chart a certain high vibration was occurring more recently. You finally discover there's an additional harmonic appearing recently. And so what we find out, doing some research with the expert, is that when a certain type of harmonic come up, means that you have the supporting bracket of the blades that have broken. Yeah, the turbine still works, but it's vibrating more than before. And if you continue, we'll continue to break others, and so on. So we know what to do, and now we need to figure out how to intervene. The intervention is based on a maintenance optimization plan, where right now, based on the recurring, ongoing preventive schedule, next week you're going to do bearing M2, loop pump, where blades are pretty much a couple of years far from now. But if you change the criteria, and you say, I'm not going to do maintenance based on foundation preventive, that is what the manufacturer either asks, you gotta change this stuff by every 2 years and so on. You do based on a predictive approach. At that point, the prioritization changes, and guess what? Next week, you're supposed to do blades. And instead, typically, all this maintenance software today is based on manufacturer requirements, because if you don't do, you are out of warranty. But if things break, because they don't take into consideration that manufacturer might have certain criteria, but if it was installed within a system that does a certain poor ventilation, or is nearby the sea with a lot of corrosion and so on, it's no longer the usual, there is some acceleration of condition. And if you have data about your situation, you will have a better uptime, reduce the cost of the diagnosis, reduce increase the OEE, that is overall equipment efficiency, and generate free cash flow. Means that compared to what you spend every year, you're going to spend less at the end of the year money to do some investments for better production and things like that. So with this one, I am finishing the overview of digital twin, and now I would like to have an open conversation on how do we work together in exploring digital twin for transformers. So I want to say goodbye to the people in the recording. Come to the next meetup on fuel and lubricant tanks.